Welcome back to the Deep Dive. Today, we're on a very specific mission.
Oh.
We want to give you a real shortcut to understanding the long-term energy storage potential in a major nation.
Okay, how?
By digging into just one really comprehensive academic source, we're pulling out the key findings on what's possible when you combine geography with sophisticated planning.
Sounds interesting. Which source are we talking about?
This one.
Ah, right. The 2019 study, a GIS-based method to identify potential sites for pumped hydro energy storage, the case of Iran.
Exactly.
Yeah, this paper set out to do something pretty ambitious. Basically, estimate the pure technical potential for pumped hydro energy storage, PHES, in Iran.
And they use automated GIS models.
They did, based on 4 different ways of thinking about the resources, 4 topologies.
Okay, so why should you, our listener, care about a technical study on Iranian energy storage?
Sure.
Well, here's the headline number, the real aha moment.
Go on.
Iran currently has about 5.1 gigawatt hours of installed PHES capacity. Just 5.1.
Right, that's the baseline.
This study, it found a theoretical technical potential reaching, wait for it, 508 gigawatt hours.
Wow.
Across 250 newly identified sites, that's nearly 1,000 times more potential. It completely redraws the picture.
It really is a game changer. And, it highlights why PHES, even though it's an older technology, is still so vital.
It's the dominant one globally, right?
Overwhelmingly. Back in 2017, it accounted for something like 96% of global storage capacity. We're talking high efficiency, 70 to 80% round trip.
And the lifespan is incredible.
Exactly. 50, maybe even 100 years. That's not like a battery you replace every decade. This is infrastructure. Crucial if you want to integrate lots of variable renewables like solar and wind.
Okay, let's zoom in on the place itself. Why Iran? What makes it suitable for this huge potential?
Well, geographically, it's perfectly set up. It's a big country, 1.65 million square kilometers.
But size isn't everything for PHES.
No, the key is the elevation difference.
Yeah.
You go from 28 meters below sea level at the Caspian Sea coast, all the way up to 500, 610 meters at Mount Damavand. That massive height gradient. That's potential energy just sitting there, waiting for the right reservoirs.
And energy-wise, I think of Iran as mostly arid.
It is largely arid, or semi-arid, yeah. But conventional hydropower already provides about 5% of their electricity.
Okay.
The issue is, with droughts and climate change, a lot of that conventional hydro is, well, underperforming. It's inefficiently used.
So PHES is a way around that, since it reuses water.
Precisely. It needs water, but not necessarily that constant, massive river flow that traditional hydro relies on. This study really leverages what's already there.
What kind of existing infrastructure are we talking about?
Well, the researchers look specifically at using existing major reservoirs, tapping into permanent rivers, and also utilizing Iran's huge coastline.
How much coastline?
About 3,000 kilometers total. You've got the Caspian Sea up north, and then the Persian Gulf and Gulf of Oman down south. Lots of options.
Okay, so they have the geography, some existing water bodies. How did the GIS model actually find the sites? What were the ground rules?
They set 2 core technical parameters that applied across all the models, all 4 topologies, non-negotiable rules.
Which were?
First, the maximum horizontal distance between the potential upper and lower reservoirs couldn't be more than 20 kilometers.
Okay, keep them relatively close.
Yep. And second, a minimum elevation difference, the head, of 150 meters.
That 150-meter head, why that specific number? Why is head so critical?
It's absolutely fundamental. The head directly drives the energy potential and the efficiency. Think of it like water pressure.
Okay.
The higher the column of water you can create between the upper and lower reservoir, the more gravitational potential energy you have stored.
Got it. More height, more power, basically.
Exactly. And it means you need less water volume to store the same amount of energy compared to a low head site. It just makes the whole system work better, more cost effectively. That's why they set a minimum.
Makes sense. Right, let's get into these 4 topologies they modeled. Topology 1, or T1, sounds like the most obvious starting point linking existing reservoirs.
It was the simplest concept, yeah. Take the 39 existing major reservoirs and see if any pair could work together as an upper and lower.
Yeah. Did it yield much?
Almost nothing new, actually. Only 2 pairs met the distance and head criteria.
Really? Only 2?
Yeah. But one of those pairs was incredibly important.
Why?
Because it was the location of Iran's existing PHES plant, the Sayabish facility.
So the model worked. It found what was already there.
Exactly. It validated the whole approach. If the GIS model correctly identified the known site, they could be confident it could find new unknown ones using the same rules.
That's clever validation. What about the other pair it found?
That one was interesting, a huge estimated potential, nearly 1,400 GWh, but
There's always a but.
it had a relatively low head, just 178 meters, barely over the minimum, and it was right at the maximum distance limit, 20 kilometers, so massive potential, but maybe not the most ideal specs.
Okay, so T1 validates the model, but doesn't unlock huge new capacity. They needed broader searches.
Right. That leads us to T2 and T6, which turned out to be the heavy hitters.
Let's start with T2, existing reservoir to a new reservoir.
Correct. T2 takes an existing reservoir, treats it as the lower one, and then the GIS scans a 20-kilometer circle around it,
Looking for what?
looking for a suitable spot to build a new upper reservoir. The key requirement was finding relatively flat land, a slope less than 5%.
Flat land up high. That sounds counterintuitive.
Well, flat enough to build a cost-effective dam and reservoir basin, you need that relatively level area to contain the water, and the new upper reservoir had to be big enough to hold at least 1 million cubic meters of water.
1 million cubic meters. Okay, so T2 is about enhancing existing assets. What about T6? That used riverways.
Yeah, T6 was designed to cast a much wider net because, there are only so many major existing reservoirs to work with for T1 and T2. So for T6, they identified 276 specific points along permanent rivers. Each point acted as a potential lower reservoir site.
And then scanned uphill from there.
Exactly. Scanned uphill within that 20-kilometer radius, looking for a suitable location for a new upper reservoir, again meeting the head requirement. Because rivers stretch all over the country, this approach naturally generated the most potential locations.
Which explains why it yielded the highest raw potential later on.
Precisely.
Okay, and the final one, T4. This is the really novel one, right? Seawater PHES.
It really is, especially for a region often concerned about freshwater scarcity.
How does that work? The sea is the lower reservoir.
That's the concept. The sea, either the Caspian or the Southern Gulfs, acts as a practically infinite lower reservoir. No need to build one.
So the model just searches inland from the coast.
Yep. It assessed over 3,000 kilometers of coastline, looking for suitable high elevation spots nearby to build the upper reservoir.
That seems incredibly useful for coastal areas needing power.
Absolutely. And because the lower reservoir, the sea, is so vast, they actually relaxed the requirement for the upper reservoir size a bit.
How much smaller?
For T4, the minimum required volume for the new upper reservoir was only 100,000 cubic meters, 10 times smaller than for T2 or T6.
Okay, 4 different ways to find sites. But these are just theoretical points on a map initially, right? You needed to weed out the impossible ones.
Exactly. That filtering step is crucial. You go from a theoretical potential to a technical potential by removing sites that just aren't feasible in the real world.
What kind of things got filtered out?
Several layers. Anything within 500 meters of towns, villages, or important UNESCO World Heritage sites was removed.
Sensible. Protect people and heritage.
Also, a 200-meter buffer zone around major roads and railways. You don't want to build a massive dam right next to critical infrastructure.
Yeah.
And perhaps most significantly, any potential site that fell within nationally or internationally designated protected areas, national parks, nature reserves, that sort of thing, was completely excluded. They used the World Database on Protected Areas, the WDPA, for that.
So that leaves you with the technically feasible sites?
Yeah.
But are they all equally good investments?
No, definitely not. And that's where the next layer comes in. Economic sensitivity analysis.
How do they rank them?
They used a well-established multi-criteria decision-making tool called TOP-PISAS.
TOP-PISAS, what's that stand for?
It's the technique for order of preference by similarity to ideal solution.
Okay, fancy name. What does it do?
Essentially, it lets you rank options based on how close they are to an ideal scenario, considering multiple, often competing factors at once.
Competing factors like what?
Like wanting a site with a really high head for efficiency,
All right, we talked about that.
but also wanting it to be close to the existing high-voltage power grid to reduce connection costs, or close to roads for easier construction access, or in an area with low earthquake risk.
Ah, so it balances all those trade-offs. How many factors did they use?
They used 7 key criteria in their TOP-PSI's model.
Let's hear them.
Okay. Number 1, and the most important, was the head of the site, that elevation difference. It got the highest weight, 0.25.
Order of the total weight just on hit. Wow, okay.
Then the area of the site, distance from the potential lower reservoir, earthquake risk level,
Makes sense.
distance from the high voltage grid, distance from the nearest road,
Uh-huh.
And finally, distance from the nearest major consumption center, like a city. That one actually got the lowest weight, only 0.05.
Interesting that proximity to cities was weighted lowest. Why prioritize head over, say, being close to where the power is needed?
It comes back to the long-term engineering and operational costs. A high head fundamentally makes the PHES plant more efficient and often cheaper to build per unit of storage capacity.
Right.
That inherent physical advantage outweighs the transmission costs saved by being slightly closer to a city, especially over a 50 or 100-year lifespan. The core engineering is paramount.
That logic holds up. Okay, so after filtering in this top PSIS ranking, what did the final results look like? We know the grand total was 500 and 108 GWH.
Right.
But how did it break down by topology, both in terms of raw volume and that economic ranking?
Okay, for pure volume, T6, the Riverways topology, came out way on top. It contributed 3,105 GWH. That's over 60% of the total potential from 163 feasible sites.
Huge number. Who was second?
That was T2, using existing reservoirs as the lower source. It yielded 1,683 GWH from 32 feasible sites.
Still very significant.
Yep.
And the seawater, T4.
T4 added another 320 GWH. Interestingly, about 88% of that T4 potential was found along the southern coastlines, the Persian Gulf and Gulf of Oman, rather than the Caspian.
Okay, so T6 gives the most sheer volume. But what about the TPSI scores? Which sites look like the best bets economically?
And this is maybe the most important strategic finding for planners. While T6 offered more quantity, the T2 sites, the ones leveraging existing reservoirs, consistently achieved much higher TPSIS ranks.
So more bang for your buck with T2, potentially.
That's the implication, especially sites identified in certain regions, like Khuzestan province, which has a lot of existing dams.
Why would T2 rank higher?
It likely comes down to piggybacking on existing infrastructure. Those large reservoirs often already have good road access and are relatively close to high-voltage grid connections simply because they were major projects in the first place.
Compared to maybe a remote river point identified by T6?
Exactly. A random point along a river might be geographically perfect in terms of head, but miles from a decent road or a power line, making it much more expensive to develop initially.
So T6 offers widespread potential, but T2 offers potentially quicker, more cost-effective wins.
That's a great way to put it. Volume versus high-ranking feasibility.
This really connects directly to national energy planning. That total potential, over 5,100 GeV each from T2, T6, and T4 combined, it's just enormous.
It is. And to put it in context, other research has estimated the amount of short-term energy storage Iran might need by 2050 if it were to transition to a 100% renewable energy system.
What's that estimate?
Around 1454 GeV.
Okay, so about 1,500.
Right. The technical potential identified in this study, the 50108 GWH,
Is way more.
it's about 3.5 times more than that projected 2050 demand.
Wow. A 3.5x buffer based purely on PHES technical potential. That's incredible breathing room.
It provides a massive buffer, yes, a huge pool of potential grid stability using domestic resources.
Which really underscores the point about PHES versus, say, batteries. Batteries are obviously key, especially for short-duration needs.
Absolutely. They're often the most cost-effective choice for short-term balancing right now.
But for long-duration, large-scale storage, this study shows PHES isn't just an option for Iran, it's a profoundly feasible one. It uses their specific topography, local materials for construction.
And it lasts. That 50 to 100-year lifespan is the big differentiator. It's building a permanent energy asset.
Building it using the landscape itself.
Exactly. It avoids long-term reliance on global battery supply chains, potential material bottlenecks. It leverages what the country physically has.
So we've really drilled down into this paper. A GIS-based method to identify potential sites for pumped hydro energy storage. The case of Iran.
We have.
We've seen how the GIS modeling, across those 4 topologies, including seawater, quantified this staggering technical potential of 500 to 108 GWH.
And the core message for decision makers seems pretty clear from the analysis.
Yes.
The T2 approach, transforming existing reservoir sites, likely offers the highest concentration of cost-effective, high-ranking projects to start with. Get those going first.
While keeping an eye on the bigger prize.
Exactly. While the T6 approach, developing new sites near rivers, provides that massive volume needed for the long-term, strategic build-out of storage capacity. You need both perspectives.
Okay, so let's leave our listeners with a thought to chew on. We know PHES can offer a structural lifespan of maybe a century, far longer than any battery currently available. So how should nations, especially those like Iran with this kind of favorable geography, balance the immediate appeal and often lower initial cost of short-term storage like batteries against the long-term energy security, the domestic control, and the sheer permanence offered by building these geographical assets like pumped hydro. What does that balance look like over the next 50 or 100 years?
That's the multi-billion-dollar question, isn't it?
It certainly is something to think about until our next deep dive.